Do you want to harness the potential of reconfigurable computing? Do you want to eliminate long compile times and the need to use obtrusive vendor tools? We have a solution for you, and it's called GReasy. GReasy is GNU Radio made easy, with FPGAs in the loop. GNU Radio is a toolkit that enables radio designers to rapidly prototype software-defined radio applications. Since it's in software, it relies on general-purpose processors to do the bulk of signal processing. These can provide flexibility, but lack performance that can only be matched by application-specific hardware. Reconfigurable hardware, such as FPGAs, bridge the gap between general-purpose processors and ASICs. Introducing FPGAs to the GNU Radio flow can solve this performance problem and broaden the capabilities of GNU Radio. Incorporating FPGAs into a workflow can slow down productivity and introduce long turnaround times. GReasy utilizes a rapid design assembly flow, making long turnaround times a thing of the past. Components of a design can be pre-compiled and stored into a module library at the bitstream level. When an application designer is ready to load their design onto hardware, all that's required is placing those modules into an empty area of the device, called a sandbox, and stitching together those pre-compiled bitstreams in a matter of seconds. The back-end tools, which enable the rapid design assembly, are generic and can be integrated into any front-end interface or application space, not just GNU Radio. GReasy's rapid design assembly can support the Xilinx Vertex 4, Vertex 5, and 7 series devices. Our most recent developments have been on the specific Kintex 7 based platform, the USRP X310 from Edis Research. Edis Research is currently in development of a modularized FPGA framework they call RF Network on Chip, or RF NOC, which when combined with GReasy can prove to be an incredibly powerful resource for designing radio applications. RF NOC comes with many advantages over traditional hardware design. Despite this, the workflow of creating a design with RF NOC blocks still relies on the traditional Xilinx compilation, which can take hours to compile a single design and generate a programmable bitstream. Our work has focused on adding this RF NOC module library into GReasy to enable rapid design assembly of these applications, making hardware design easier and boosting productivity more than ever before. What better way to illustrate how easy it is to use GReasy than to show the tools in action? Here we have GNU Radio Companion. On the right is the list of functions in the GNU Radio block library. If we navigate down here to UHD, which stands for USRP Hardware Driver, we can see the RF NOC blocks available to the user. Edis Research has developed an out-of-tree block library for GNU Radio, which enables the user to target RF NOC blocks in the GNU Radio flow graph. We've extended this block library to call GReasy's back-end rapid design assembly from GNU Radio. We'll start by building a simple example that passes data to the USRP into an RF NOC FIFO block. Here we have a blank flow graph. By default, GNU Radio Companion generates a variable block, setting our sample rate to 1 meg and an options block which specifies the name of the GNU Radio Python script. To use the USRP with RF NOC, we need to locate the device 3 block, which starts the USRP hardware driver. We've modified the device 3 block to run GReasy's rapid design assembly flow and generate the bitstream before sending and receiving data from the USRP. For the device 3 block to call GReasy, we're also going to need these import blocks, which import some Python libraries for us. Let's next grab the RF NOC FIFO block. Simply navigate to the UHD and RF NOC and select the FIFO block. Next, we need a data source and sink. Let's get a signal source and add some noise so we can see some activity on our sink. We'll also want a throttle block to set our sample rate. Finally, let's get our data sync and connect everything together. That's it, our flow graph is built. Now let's execute the flow graph and see what happens next. First, GReasy calls a UHD tool to check if the device is already programmed with the RF NOC blocks we want. It didn't find the blocks, so now GReasy rapid design assembly begins. After a short amount of time, a window will pop up labeled Module Shape Visualizer. This displays the RF NOC modules that have been successfully placed on the FPGA in the sandbox region of the device. The rapid design assembly should finish in about 30 seconds, depending on your machine's resources. See here that we now have a simple sine wave streaming to and from the device, routed through a rapidly compiled RF-NOC FIFO block. I've already built this next example flow graph. I'll go ahead and click Execute to begin the GReasy rapid compilation. In this example, I'm passing data to the USRP just like the previous example, but compiling a design with an RF-NOC FIR filter and an FFT block in addition to the FIFO. Data passes through all three blocks and back to the GNU Radio host. GReasy is finished and the device is programmed. The output data has been filtered and then analyzed by the FFT block. Finally, I'll show an example with an RF-NOC window block. Just like the previous example, the flow graph is already built. I just need to execute it. The bitstream has been generated and programmed, and you can see the output data is being processed by the RF-NOC window function block. That wraps up this video demonstration. As you can see, GReasy is a tool like no other. The domain that GReasy has currently explored is narrow, but with proper support, the rapid design assembly backbone of GReasy can be integrated into more tools and exposed to a wider audience, enabling rapid design assembly of hardware and increasing productivity of designers in a multitude of applications.